Okay, for the first part, we need to know what is the shortest path from the city to the suburb. So we have we can do it with an injection. We have an injection here of 1, and we have an individual that starts at the city and then goes to the new suburb and has to go through these other suburbs in between. And we presumably are given the distances between adjacent suburbs. So we need to decide whether this is the way to go. And like usual, we know that the answer will be integer. So we just need to have the distance between every adjacent. So this would be the distance between, let's say, let's make this 1, make this 2, 3, 4, 5, 6, 7. And so this will be D1, 2. And similarly, this will be 0, 1, D2, 7. And we want to overall minimize. And at this point, it becomes a mechanical matter then to put the file into the AMPL, create a .dat, and run it. The one warning here is that you really need 2 separate arcs. So we cannot have a double-headed arc. So you would need you need 2 arcs, because we don't know which way we're going to go. Are we going to go from 1 to 4 and then go that way, if that is ever optimum? So you have to get rid of 2-headed arcs, which we just did, and the rest can be filled in, and I consider this problem solved. Thank you. If we want to look at the this fastest way, we need some more data. So this is the city and the new suburb, and in which case the distances is not enough, but we need the speeds and the distances. So we'll have that speed is equal to distance divided by time, and we really want the fastest route, so we really need that the time, the Tij, go from node I to node j, will be equal to the distance Ij divided by the speed Ij. So we'll have the maximum speed limit for each one. We can calculate these in advance, and so now the problem is just slightly different. It's Tij, which one gets me from 1 to 7 in the fastest possible time. Otherwise, the problem remains identical. Now, looking at the third part, which is the maximum capacity, we will have the maximum capacity per link. So let's say that the let's call it cap Ij is the maximum number of cars traveling from I to j in rush hour. So we know for each link how many there are. Now how do we label this diagram? Well, clearly the capacity is a maximum, so we have any number of cars can go through here, and this is the capacity 1 to 2. We don't know yet what to put for our driver. And the other thing is that we don't know at this point how many cars. It's clearly more than 1 car can go through here. So how many cars can go through here? We don't know. And because we don't know, we need to make this a circulation flow. So as many, and this we covered under the maximum flow kind of problem. It's a maximum flow problem. On the way back, we can have any 0 to infinity. There's no limit. But then we're going to provide an incentive of, let's say, $1 per car. So we're going to try to maximize the total number of cars that go through the back loop. And that's really the same thing as the number of cars that can go through the forward loop. And with that, now we have only one part missing, is we don't know what to put for the incentive. And we're going to put 0, because really we don't want to bias which routes the algorithm should take. And so the algorithm will then select which routes to take that will maximize the flow back, which has an incentive. And that solves it. So for the set of data that is given in the problems, you can then solve this problem, again, either by solver or using Apple. Okay, that's that for problem 2.